the center of gravity. The weight W of an extended body is the vector sum of the gravitational force acting on the individual elements, the atoms of the body. Instead of considering all those individual elements, we can say that a single force W effectively acts at a single point called the center of gravity of the body. By effectively, we mean that if the forces on the individual elements were somehow turned off and the force W at the center of gravity turns on, the net force and the net torque about any point acting on the body would not change. Look at this. This is the 1 point. Around this O, we have a torque I equal to distance xi and fgi. This is some point. Okay? And then we see the total net charge is sigma tau I, sigma xi fgi. Okay? Body as a whole, this is body as a whole. You have a tau equal to x com, this is x com, and fg. This fg is sigma f. Okay? This is a net torque. They are the same. We look at it in different point of view. Okay? So they should be the same. That x com sigma fgi equal to sigma xi fi. And this one, we know that fgi is mig. This is mig. If all the g are the same, gi are the same, okay? And then we can cancel out this one. What we got? We got x com equal to sigma m and sigma xim. What is this? Actually, this is the definition of center of mass. Okay? This is the definition of center of mass. They overlap. The condition is OG is constant. If G is the same for all elements of a body, then the body's center of gravity is coincident with the body's center of mass. In Fig A, a ladder of length L, 12 meters, and mass M, 45 kilograms, leans against a slick with a flickless wall. Its upper end is at height h 9.3 meters above the pavement on which the low end rests. The pavement is not frictionless. Okay, they have a friction. Okay. The ladder's center mass is L/3 from the lower end. It's not uniform. Okay. A firefighter of mass M, 72 kilograms, climbs the ladder until her center of the mass is half L from the lower end. What then are the magnitude of the forces on the ladder from the wall and the pavement? We know that this wall on the top is frictionless. What does this mean? This means no friction along this vertical direction. So the force acting on the ladder by this up wall is perpendicular to the wall because no friction, no force along the wall, vertical wall. And in the bottom is friction. It has friction. So it has horizontal friction and vertical normal force and so on. So that's the difference. Okay? Now let's see. This A. This A equal to L squared minus h squared square root. Okay? And then we take point O. This is the point O as a reference point. We see what's happening. We have two things. Sigma f equal to 0, sigma tau equal to 0. Right? Let's see sigma tau equal to 0. How many forces are there? Is that 1, 2, 3, 4, 5. Among these 5 these two forces, their torque is 0. So they do have a force, but they don't have a torque around. Oh, that makes things easier. So we get FW, this one. FWH, this is clockwise, so it's a minus number. And this mg, okay, half A. This is a middle, so it's half A. This is this around, so there's a positive. And small mg, okay, the letter is 1/3. This is anti-clockwise, a positive. And these two forces, they have a force, but they don't have R. So this is 2, 0. Okay? So from this one, I can get FW equal to GA half M. It's very easy to find. Okay? Once we know this one, then we know sigma F equal to 0. Okay? Then we see X we have two forces. One is this, one is this. So this one is easily equal to this in magnitude. Okay? So it's 410. Now let's look at this one. The net force on y direction is 0. We know big mg, we know small mg, we can find this one. Okay, this is the 2. Okay? Then we get everything. Sample. In the figure, a rock climber with mass 55 kilograms rests during Chitmi climb, pressing only with her shoulder and feet against the walls of a fissure of the width, this is the width, 1.0 meter. Her center of mass is a horizontal distance D, this is D, 0.20 meter from the wall against which her shoulder are pressed, this is the one. The coefficient of static friction between her shoes and the wall is, this one is 1.1. And between her shoulder and the wall is 0.7. Oh, it's different, right? To rest, the climb wants to minimize her horizontal push on the wall. What is this push on the wall? Minimize. The minimum occurs when her feet and her shoulders are both on the verge of sliding. That the force, you put it harder than if you stick. What the minimum is, they're just about to sliding down. So in this case, friction is limited. Okay. A. What is the minimum horizontal push on the wall? N. B. For that push, what must be the vertical distance H? This is H between her feet and the shoulder. The feet and this is H. Okay. If C is too stable. See the question A. How many forces accumulate? We see the net force Y equal to 0. How many net force? No. F1, F2, and mg. Okay. And then F1 is mu and F2 is mu. These two forces are the same. Why? Because you look at this balance along x direction, sigma F equal to 0. These are the two. Okay. Also, so in this case, I get a normal force should be mg over mu plus m. You put this together, you get this one. Right? Yeah. From here. Next, B. What will be that? We see the minimum torque Z equal to 0. This is the point that we take a reference. Okay, so these two cancel out because they don't have a torque, right? Only 1, 2, 3. Then we find C. About the point O, we have F1. This is a clockwise, so it's minus F1W. And this one is anti-clockwise, it's positive, and H. And this one is going down, you see, so it's D, okay, DMG, plus these two zeros. So that's very simple. Then we can get it answer. H equal to F1W minus mgd over n. Okay? And F1 is mu1n. Okay? Then we get 0.70.
This boom arm is supported by a wire that is attached to a spring scale. The scale shows the tension which is necessary to support the arm. The arm has a mass of about 2.2 kilograms. Now we'll add 2 kilograms to the arm. Here is the new reading on the scale. Now we'll put 4 kilograms on the arm. Here is the new reading. Now we'll move the pulley holding the wire to a new position. Here is the reading on the scale with the arm empty. Here is the reading with 2 kilograms added.
Do the forces supporting the ends of a bridge change as a heavy bus moves along the bridge, or are they always the same? This demonstration uses a model bridge supported by spring scales and a heavy toy truck to find out. When the bridge is empty, both scales supply the same force to support their end of the bridge. If the truck is placed in the middle of the bridge, the scale readings increase, but are still equal. What if the truck is now moved to the right? Will the scale still show the same reading? The force provided by the right scale increases, and the force from the left scale decreases. As we move the truck closer to the end, the difference continues to increase.